Okay, hi everybody. Welcome to what should have been last week's live stream. I am so sorry about that for all of you who came. Unfortunately, I got sick and took NyQuil in the middle of the day and just passed out, so I'm very sorry, but thank you all for coming tonight. To kind of make up for that, I'm just going to put the Google form in right now. I will continue to have a live stream this Friday. It's going to be a Q&A so that you can come and ask any questions throughout the term of material that maybe you just want to talk about or have more clarification. But with that being said, today we're going to be talking about population ecology and community ecology. So let's get started. Okay, so we're going to use salamanders and their parasites for the first part of this exercise. So, a researcher has recently discovered 3 species of parasites that infect developing salamanders. He suspects that one or more of these species cause fatalities during salamander development. To test his hypothesis, the researcher sets up a series of experiments. In each experiment, he varies the density of the salamander populations. He infects 2% of each test population at the start of the experiment and measures the mortality rate after 4 weeks. To establish a baseline mortality rate, he sets up a control experiment that differs only in that no parasite was introduced at any density. The data table and graph below relate to the mortality rate of salamanders caused by 3 different parasites to the original density of the developing salamander population. So we can see down here the data that they got from their studies, including the density and death rates of the populations A through D, which include D as the control. And that is shown in this graph here. So we're going to take the given data presented and use that to answer some following questions. So A, given the data presented in the graph, indicate whether each of the parasite species is acting in a density dependent or density independent fashion. So we previously talked about density dependency and independency, meaning that when density increases, that something either decreases or increases. That's density dependent. So when the density changes, that factor changes. Independent means that no matter the density, it stays the same. So looking at this graph, we're going to continue. Also, thank you for in the chat how I'm doing. I'm doing fine, a lot better. I was really sick on Friday. It just kind of came in a wave, so I'm so sorry again for missing. But I'm feeling better. I still just have congestion. I'm quarantining. I'm doing all the things, but enjoying the nice day from my windows open. So thank you for asking. So A, given the data presented in the graph, we're going to indicate if it's density dependent or independent. So if we're looking at parasite A, which has the little triangle, we're seeing as density increases, this guy also increases. I'm going to erase that, but we can just write that down as parasite A is density dependent. So increased mortality rates with increased density. Thank you guys. You are all always so nice. Really appreciate you. Reminding again, I will also be here on Friday from 2 to 3, the original time for like a Q&A, in case you guys want to come. So then looking at parasite B, and just going back to our graph real quick. Parasite B is up here, and we can see that it stays relatively constant over the range of density. So we can say that it is density independent because mortality rate stays consistent over varying densities. And then finally, well, not finally, but we know that line D is control. So the final parasite we're looking at, C, if we just go back to that graph. And now we're looking at C, which is this guy. We see that it kind of decreases, increases, decreases. There is not a consistent, it increases with density, or it just stays consistent. It kind of acts on its own. So what we would say for that is that it doesn't fall into either category, and that's totally fine. So we just say neither density dependent nor independent. I don't know why I have the urge to always spell dependent with an A, but I'm not majoring in English, so. And then finally, D, which is control. I'm just going to put that in parentheses. If we look at it down here, we can see that D is pretty consistent, and so it is density independent because it shows the same mortality regardless of density. Okay. And then B, after looking at the data for parasites A and B, develop an argument to indicate which is more likely to cause extinction of the salamander population. So we showed in A that parasite A is density dependent, so it increases mortality rate with increased density, and B is density independent because the mortality rate stays consistent over varying densities. So, because of the overall high mortality rate at all salamander densities, parasite B may decrease the population so much that it actually can't rebound. So if a population is so great and parasite B stays consistent, which means that it stays consistent throughout the increase, it may actually take away enough where that population can't replenish itself. Whereas parasite A has a lower mortality at lower population. And so you can see a population size increase and then parasite mortality increase over time. So only at very high population densities can parasite A cause extinction, but parasite B has an equal chance throughout the densities of this population. So I'm just going to write it down in summary for you. Okay. What models can you use to calculate how quickly a population can grow? So this is the population growth model. Delta n over delta t equals r max n. And so I'm just going to write out what the terms mean, and we can use that further to solve some problems. So delta n means the change in number of individuals. So n is number of individuals. Okay, and then delta t is the time interval during which the change of the number of individuals occurs. So I'm just going to say change in time of change in individuals. I'm sorry, just 1 second. I just have to blow my nose. And then R max is per capita population growth rate. N is initial population size. This can also be seen as N naught, and not just meaning a subscript 0. So then answering B, what type of population growth does this equation describe? So as you can see here, all we're seeing is the number of individuals, the time it takes, the growth rate, and what the population size was initially. So we're not seeing extinction rate, we're not saying immigration, nor immigration. So we're not seeing any factors that might limit growth rate. And so what we're seeing here is exponential. this is under the assumption that there is no limiting resources. We have an unlimited supply of food, that sort of thing. So that's what exponential means. We would call this J-shaped, curved. Because we see and then C, what assumptions are made to develop the equation? Like I kind of hinted before, there is unlimited space and resources. Okay, moving on. Population growth may also be represented by the model delta n over delta t equals R max n, and then parentheses k minus n over k. What is k? So k is equal to carrying capacity. And this is just the number of individuals that can be sustained over time. It is a function of the environment. And then it says, if n is equal to k, what is delta n over t? So when n is very, very small, the population grows exponentially. So the actual number of new individuals added is relatively small, but because n is so small, as n nears the value of k over 2, delta n over delta t approaches maximum. So as n is closer to k, delta n over delta t decreases. And so when answering C, it is pretty similar to B in that, so we know that delta n over delta t is equal to no change in the population if it's equal to 0. And so similarly to said above, when n is much less than when n is very, very small, the population is growing exponentially. So when the change of individuals is small, or the number of individuals is small, we have a lot of room to reproduce, to add to our numbers of individuals, and so the actual number of individuals added is small when the population is growing exponentially. And so because n is so small, when it nears the value of the carrying capacity, when k over 2, so if we say, all right, okay, I'm taking, okay, so I'm going to put k on the graph increasing. And if the number of individuals, and if this is increasing, is reaching this half point of carrying capacity, then this delta n over delta t is actually approaching its max. So what it's saying is, as the number of individuals approaches k, the carrying capacity, this delta n over delta t will decrease. So let's say this is half, and as it increases, it's going to start to grow exponentially, but then eventually it's going to start to kind of level off, maybe in some cases go above, but it's just saying that this exponential growth does not really occur forever, and it can level off. So that's what it's asking. And then for D, what assumptions are made to develop this equation? We're looking at logistic versus exponential, and so the logistic model assumes that space and resources are limited. And so these factors determine the maximum number of individuals that can be sustained over time. Okay, 3. You and your friends have monitored two populations, population A and B, of wild lupine for one entire growing season, which is June year 1 to June year 2, so just 12 months. By carefully mapping, tagging, and censusing the plants throughout this period, you obtain the data listed in the chart. We have the initial number of plants, number of new seedlings established, and number of the initial plants that died. 500, 120 for A, 300, 30, and 100 B. No problem, do what you gotta do. I know this is late for everybody, so no problem. So using this information, we just need to calculate the parameters for each population. So B, we're looking at number of births and deaths. So we see here, new seedlings established is 100, and the number of initial plants that died is 20. So therefore, there we would have a full 100 new births, 20 deaths. For population B, we have 300 initial plants, we have 30 new seedlings, and 100 plants that died. So 100 for deaths and 30 up here. For lower B, we would have 100, 30, 20, 100, and our max 0 and 0. So given the initial population size and assuming the population is experiencing exponential growth at growth rate r, what will the number of plants be in each population in 5 years? Use the initial population sizes times 0 and compute to time 5. So we talked about earlier the change in number of individuals over change in time is equal to an R max with N. And if it's exponential growth rate, we would just say that R is 1. Sorry, I'm about to sneeze. I'll be right back. So, you guys hear me? Because I feel like my mic might be coming out. Hello? Can you guys hear me? Trying to fix stuff. It tells me that. Okay, you guys, you can hear me? Okay. Sorry, everybody, for the population. So using the equation that we saw earlier that has, because this only gives us births, deaths, and then lowercase b and d and R max, and we have R max as 0. We have delta n over delta t is equal to R max n. And so it's asking for the number of plants being each population in 5 years. So it's asking for n. For population A, delta n is 100 minus 20. And R max is 0. Delta t is 5. sorry, 1 second. Because we have to account for established. So, we have 100 plus 100 minus 20. Okay, for some reason, the answers I got earlier were 10, 15, 81. Just give me 1 second. I'm so sorry, everybody. Just not adding up on my calculator. Okay, we'll come back to this. I'm sorry to do this. But the math is not adding up, and I want to make sure that you guys get the rest of the material. So I'm going to put the form in one more time, and we're going to go to 4. So using the exponential growth formula, you can determine the amount of time it will take for population to double in size if you know R max or R. The doubling time is equal to log 10 2 over log, TED 1 plus R. Alternatively, this value can be estimated by using the formula 70 divided by the percent increase per unit time is equal to doubling time per unit time, or 70 divided by R, which is equal to what is the approximate doubling time. Using either of these formulas, the exponential growth formula or the approximate doubling rate formula, calculate the following. If the population of a country is growing at 2% per year, how many years will it take for the population to double? So if we had 70, what this is saying up here is 70 divided by the percent or increase per unit time, which is then equal to the approximate doubling time. So this would be 70 divided by 2%, which is equal to 70 years. And B, if your bank account is growing at a rate of 1% per year, how many years will it take for your money to double? So using the same equation, doing 70 now over 1%, this is now equal to, oh, I'm so sorry. My math today, my math. Okay, so 35 years. 70 divided by 2%, which is also 0.02, is equal to 35 years. 70 divided by 1%, which is 0.01%, is equal to 70 years. So this up here is just the increase. Excuse me. Five. You are studying the growth of a particular strain of bacteria. You begin with a tiny colony on a petri plate. 1 day later, you determine that the colony grew and exactly doubled in size. A calculation showed that if the colony continued to grow at the same constant rate, it would cover the entire plate in 30 days. Assume colony size is directly proportional to the number of individual bacteria. What is the value of R? So we know the doubling time is log 10 of 2 divided by log 1 plus R. So we know the equation has to do with 70 divided by the percent increase per unit time, which is equal to the doubling time. So if 70 divided by R is equal to 1 day, then R must equal 0.7 or 70%. And B is asking, what day would bacteria cover half the plate? If the bacteria colony doubles in size every day and completely covers the plate on day 30, then it must cover half on the plate on day 29. Six, you collect data on birth and mortality in 3 populations of grasshoppers and calculate the following birth and death rates for these populations. Both populations are experiencing exponential growth. So we have this data here. And so we're going to do true or false on A through D of question 6. So population A is growing the fastest rate. So that's false. The death rates are actually 80%, and so that is way higher than B or C, and so it actually does not qualify for having the fastest growing rate because 80% of those individuals are dying off. And B. Population C has the lowest death rate, so that is true. We see here 0.05 is lower than 0.8 or 0.35, so that's true. C is growing at the slowest rate. That's actually false. The death rate is the lowest, and just because the birth rate is the lowest doesn't actually mean that it's growing the slowest. Usually we would look at death rates and how each of these guys, I know that I'm drawing a lot. 1 second. So each of these guys, 8 and 3.5, are 0.1 away from the birth rate. So they have the equivalent rate of growth, whereas this guy has the same birth rate, but it's still significantly larger because of how low the death rate is. If that doesn't make sense, just let me know. And then D, all populations are growing at the same rate. So this is true, and that's why I kind of wanted to confuse you guys a little bit. So all of them are 0.1 away of death and birth rate. So technically, all of these were trick questions because A is not growing faster than B nor C. C is not have a lower death rate than B or A. C is not growing slower than B or A, and all populations are not faster or slower than each other, so they are actually all going, their birth rate and death rates are the same. 7. In a herd of bison, the number of calves born in 1992, 3, and 4 was 55, 80, and 70, respectively. In which year was the birth rate the greatest? So we only know the birth rate And so actually we can't answer this. So we need to know the population size to answer. A population of pigeons on the west side of town has a per capita annual growth rate of 0.07. A separate population of pigeons on the east side of town has per capita annual growth rate of 0.10. If the populations are both growing exponentially and both are censused the following year, in which of the populations will delta n over delta t be greatest? So we don't know n naught, which means we don't know how large initially the populations are. So we can't determine which ratio will be greatest, because if the two populations are equal, or if the population on the east side is larger than the west, delta n over delta t will be greater on east side. But if initial population on west side is large, then vice versa will happen, right? So we don't know n naught, and so therefore not enough information is given to answer. Okay, 9. We are to fill in the missing data table for A. This graph has age class, survivors, deaths, mortality rate, and number of offspring. We can kind of use these and these as a guideline. And so using mortality rate, we can multiply that by the survivors to get the deaths. So if I multiply 0.33 by 90, which is approximately 1/3, I get 30 deaths. If there are 30 deaths out of 60 survivors, then I have a 50% mortality rate, which is 0.5. If the number of deaths that occur is 6 and the mortality rate is 100%, then the survivors are 6. So it's just about kind of algebra, going through it and multiplying. All right, B. Owing to a good food supply and a small predator population, the rabbit population is growing by leaps and bounds. The rabbits call a meeting to discuss population control measures. 2 strategies are proposed. 1, delay all rabbit marriages until the age class 2 or 3. And 2, sterilize all rabbits in class 3 or 4. Which of the proposed strategies will be most effective in slowing the population growth? So for B, in the first 2 years of the rabbit's lives, each reproduction pair has an average of 1.5 offspring. For a cohort of 100 rabbits that are in age class 0 to 1, 90 or 45 pairs of rabbits will each have 1.5 offspring approximately. So during years 1 to 2, they will add about 67.5 rabbits to the population. So when this same cohort reaches the 3 to 4 up here, it will have 30 rabbits or 15 pairs that will produce an average of 2.5. So 2 to 3, that middle guy, will have the most effect if they were limited by delaying rabbit marriages. Okay. Now this is dealing with logistic growth, and it uses fisheries as an example. So suppose you have a farm on which you grow, harvest, and sell edible freshwater fish. The growth of the fish population is logistic. You want to manage your harvest to maintain maximum yields, which is maximum rate of production from your farm over the number of years. As a fisheries manager, you are responsible for deciding how many walleye can be harvested without destabilizing the population. Below is a data table showing the walleye population in a typical pond on your fish farm over 24 weeks. Draw a graph showing how population size on the pond changes over time. So, lucky for y'all, I've interpreted this data table, and we have this graph that corresponds. And so to answer question B, how large should you let the population get before you harvest? So what we know is that the rate of production is fastest where the curve on the slope is steepest. So around here we have the steepest slope. Steepest slope. So this would be around point C. Has the highest number of production of individuals. And so another little thing is like we have population over time. So this graph is NT over delta T. So we're seeing where this value is highest, where the population growth, delta T, is higher than the time interval. Okay, moving on to C. Assume the carrying capacity for your pond is 250 individuals. So that is what K is. Check your answer in part B by using the data in the chart and computing the change in the population size when the population is at several different levels relative to its carrying capacity. k minus n over k. So we have the math for this is 250 minus 25 over 250 for this column. And that is equal to 0.1. Delta n So we know that that is R max and K. So we have this value, just reminding you of the equation. This guy is equal to R max N times K minus N over K. So this is R max, which we got as 0.2 times N, which is 25, times this, which you got as 0.1, and that is 0.5. So I'm going to be using these equations to fill out the rest of this table. And for those, and if this doesn't quite stick, just let me know. All right, just a few more questions. So, what can we learn about a community of organisms by removing one species? A researcher collected data on an experiment she conducted on 2 desert islands. The islands were of similar size, climate, species composition, and richness, and they were the same distance from the mainland. Originally, the same species of snake was present on both islands A and B. In her experiment, the researcher removed the species of snake from island A. For comparison, the species of snake was not removed from island B. Since she then recorded the number of animal species on each island over a period of 24 months. And then her data is found below. So we know that A has no snakes and B has snakes. We can see this presented in these graphs where this is an overall decline and B is an overall incline. And remember, B has snakes. So 1, graph the data just as we have, and A, construct a hypothesis that explains the difference between the numbers of species present on island A versus B. So one was that the snake was a keystone species. So another competitor on Island A dominated the other species. And then B, propose an experimental design to test the hypothesis. So this would be to remove snake from Island B. Reintroduce snake to Island B. And collect data of species diversity over time. This includes population size and richness. Okay, and then so this is what I kind of mapped out for you guys. And so for B and A, B is a square. And this is reintroduced to A. So though we're seeing a decrease here, it'll increase once snake is introduced. And then this down here is snake removed. Okay, that is actually the end of today. If you guys want to check your attendance for any of this term, please just message me on Twitch or email me. I'll put my email in the chat. I will just search your name and then, excuse me, sorry, my congestion. So I will research your name and then just let you know how many sessions you've been to. But other than that, that's all I have for today. Thank you guys so much for accommodating me and for coming today. I appreciate your flexibility, and I will for sure be here on Friday to answer any questions about the term or any content, any advice, anything you guys need. And that will also be for points. So come if you need to, but if not, just message me. Alright guys, thank you so much. Bye!